So yeah, we were down here last time talking about for loops. So the idea of a for loop is you want to go through something that is iterable. You'd like to iterate through it. That just means to go through it like a list, for example. You want to go through all the elements of a list, 1, 2, 3. You want to go through every piece of a range. If you ask for a range, remember what that does? It essentially gives you back a list. And so the example that we were talking about is let's get a list from the user. We've done that. That's the very last thing we did last time. That one. I'll just save it in the same file from last time, and then I'll make new ones for everything else today. But here's what we started. So we've got a while loop so far that's just going to get a list of numbers. 1, 2, 3. Once I type -1, then it's done. It's going to add into this list L. So we have built this list L with a bunch of things in it, 1, 2, 3. And now what I would like to do is no matter what list I was given, because it could have been 1, 2, 3, it could have been 3, 1, 2, whatever I wanted to type, in any order I want to type it, I would like to find the minimum value of this list. All right, so the minimum could be anywhere. It could be the first thing, could be the middle thing, could be the last thing, wherever you want to put it, because the user doesn't have to enter these numbers in any kind of order. So what we will do is we will go through that list, all the elements, with a for loop, and we will find the minimum. All right, so again, this is what a for loop looks like. You say for, give a variable name in some sort of listy thing, like a range or an actual list. Then you say what you want to do with that element. So like every round, your variable name gets set to the next element in the list, and it keeps running the body. All right? So that's what we were doing with the for loop. So yeah, let's actually have one. So to do the minimum, right, the goal is to go through your list, have it try the 3, the 1, the 2. You make a guess first that your first element, this 3 here, is the true minimum. And then as you scan the rest of the list, you have it fight with your min variable. It's like, all right, 1 versus 3. Okay, the 1 wins. I'll put the 1 there. Now it's 2 versus 1. 1 still is right. It's still supposed to be there. So after you've gone through the entire list, you've given everybody a chance to fight out for the min, you have the real min at the end. All right, so that's going to be the setup. And so let's walk through that. So here, we've built a list. And so now, the very first step for our minimum game is we want to make a guess. Probably won't be right most times, but just guess that the first element is the true minimum. We will update that guess as necessary. Everybody gets a chance. The min is the first element of the list. I guess if you wanted to be technical, maybe the first element that you should ever, the first value for your minimum should be like, I don't know, positive infinity. You could do something like that. Make a guess that the first element of the list is the min, so I say save it in a variable called min and set that equal to L at index 0. That's the first thing, right? So we're guessing that like the 3 is the true minimum, but it's not. But maybe there was a 1 there, who knows? Maybe there's a 0 there. We'll never know. Could be the real min, might not be. And then what I want to do is loop through every element of L and update our guess. So have it fight out for whatever's in this spot for min. Right? It might be smaller. If I see something smaller, update. It's better. It's a better guess. Like when it was still 3 here and I see the 1, let's update our guess for the min to be 1, because 1 is a better guess. So yeah, that's what we'll do. I'll say for, I'm going to give a variable name for, I'll call it x. For everything, call x in L. And what's going to happen is x is going to range through every element of that list. And so now what we want to do is replace min with x if x is a better min, if it's smaller. All right, so if x is a better guess for the min should be set to x. That is what we should do here. Okay, so let's do just that. So if I see that x is smaller than my min is supposed to hold my best guess of the min so far. X is a much better guess right now. Right, it's smaller. So that means my guess for the min should be updated to be x. Now it's the smaller thing. I saw something smaller, that's a better min. Keep going. And by the end of time, by the time this loop is finished, it's gone through every value in the list, had it be called x. By the time it's finished, you see how min is going to be the true minimum, because it's always going to be the very smallest thing that always wins out. All right, that's how that works. And so yeah, now min holds the true min. Now, so there we go. We can print it. What is the min? It is whatever's in that min variable. So yeah, let's do it. Now, no matter where I put things, I can do, maybe the first element is the min. I can do 1, 2, 3. There's my list, 1, 2, 3. It's like, yeah, the min was 1. It started its guess at 1 and never updated it because 2 and 3 were bigger, right? It never hit this if statement's body. But if I rerun it, give it a different kind of list, maybe it was like 2, 1, 3, it's still going to find the min of 1 because like it's going to guess that 2 is the minimum first, and then it's going to update its guess. Like, oh yeah, 1's much better. And it doesn't matter where the smallest thing is, it will always find it. Could be the last thing. Be like, I don't know, 3, 2, 1. It will always keep updating its guess, right? Its guess was 3, now its guess is 2, that's better, now its guess is 1, that's even better. And by the time it's finished, right, it's always found the smallest thing. All right, so that's the algorithm, and that is a good use of a for loop. We're going through every element in the list from left to right, calling it x for a split second. Everybody gets a chance at being x, and we're using that to update our guess. Are there any questions about that example? It's like this is in between lectures, I guess, but hopefully it's all coming back to us. So that's a good example of a for loop. I think I have one more. All right, so let's do another one. Let's do a proof together, because you remember that code could be a proof. So let's prove the following statement with code. So here, remember how to pronounce all of this. Let's see, where do I want to be? Give me 1 second. I think I'm in the wrong window. There we go. So remember how to read this. This stands for there exists. There exists an x such that x is between 32 and 37 and, right, the and symbol, and x is prime. So I'd like to prove that that is a true statement by writing a piece of code. You see how I might be able to prove that? So I want to find one good value who can claim that there exists an x if this is all true. There's just one good value at least of x. What is true about x? It's between these numbers and it's prime. So if I find a prime number between 32 and 37, I have proven my statement. Yeah? So that can be my program. Let's search between 32 and 37. Okay? So that will be what I want here. And let's use a range. How can we pick out the numbers from 32 to 37 in a range? It's the range function. If you say range by itself, like range up to 50, like I was saying, first of all, you can't really see it very easily. It's like, it's a range. It doesn't print it very nicely. But you can convert it to a list very easily. So it's technically not a list, but it's still something you can go through in a for loop. But if I convert it to a list, you see how the range up to 50 is the number 0 to 49. So it's always one smaller than this thing that you give here. And if you want to start at something else, like 32, that's the first thing you get. So I'll say range from 32, not to 37, because that's not enough, but up to 38, because it's always inclusive on the first thing, like it includes 32, but exclusive on the last thing. So it's going to go up to not quite 38. All right, so that's how I get the numbers I care about. It's going to be a range from 32 to 38. And that will give me the numbers that I want to look through, right? Those are the ones that are relevant here. So let's go through those, and then I also need to check, like, just like find one of these that's prime. Yeah? So let's do that. Dun, dun, dun. So, yeah, 4, something like this. I like to loop through all the numbers in this particular range. So let's call them n or something. I don't know, for every number n in the range from 32 to 38, which is just 32 to 37 really, what do I want to do? Just like I've proven my statement if I found like it's automatically between 32 and 37, right? And then it's also prime. So if this number n is prime, I'll make like an is prime function. If is prime n gives back true, then I found a good one, right? Print the statement is true. Yay. I found a good one, and then I can print the number that was prime. N is prime. So yeah, and then if it doesn't print something, I'll know that it's false, right? Because then it didn't find a good one. That can be how we do that. All right, so let's make an is prime function real quick. This is a little complicated. I'll never ask you to write like an is prime function on your test. You don't have to copy that down, but just the idea is a good one. And then I'll also talk about functions in depth in just a second, because I have a spot for that on this little cheat sheet. So if you want to use this, remember you got to handwrite it onto your own cheat sheet. But here, let's do an is prime function really quick. Just like def is prime, and it will return true if the number that you give it, let's call it num, if that's prime, and it will return false if it's not. All right. So how do we check if a number is prime? I'll just do this quickly because it's something we've technically done before. It is a little complicated though, so I'm not going to force you to memorize this, but the idea should hopefully make sense as I'm explaining it. So like, how do I know if the number num that was given to me is prime or not? Well, a prime number is one that only has the factors 1 in itself. So if I try any other possible factor, like if I'm asking if like 8 is prime, I'll try all the numbers from like 2 to 8, right? Or sorry, 2 to 7, and see if any of those are factors, because if they are, that means it's not a prime number. And we'll find like 2 and 4 are factors, right? So try every factor that there could be other than one in itself. And if any of those go through properly, then it was a composite number. Yeah. So for every number n in the range from 2 up to num minus 1, right? Up to num minus 1. So I could just say num here. That would work. Or, well, let's do that for now. So those are the possible factors. And then if I find that num and n go in cleanly, if I try to divide num by n and I get nothing left over, remember that is a modulus calculation. So like, what is 8 modulus, I don't know, 2? It tries to divide 8 by 2 and gives me the remainder, right? Is there anything left over? If there's 0 left over, that means it did go in cleanly, all right? So if my number num mod n, if I try to divide it by this potential factor n, if it goes in cleanly, there's nothing left over, that means that n was a factor and n is a number other than num or 1, right? So that means it's not prime. Return false. I'm done here. And then if we get through all these numbers and we never get to here, because return just stops the function, immediately gives something back. If I get through all this, all these potential factors, and I don't find one, that means none of them worked. Like the number 5, for example. We'll try 5 mod 2, 5 mod 3, and 5 mod 4, and it never goes in cleanly. That's what it means to be prime. None of those were factors. So if I get through all of them, then it really was prime. Return true. And so that is how you do that one. I will not test you on like how to calculate prime numbers, but this idea of modulus will probably come up. All right, very helpful stuff. And so yeah, let's run it. I'll just do 42 empty list there, and it looks like it found that the statement was true because we had 37. The very last option was a prime number, so that proves that this statement is true because there's one good value at least of x. I guess there's only one good value of x here. It is 37. X is 37. This is true about it, and this is true about it. We are good. All right, so that's how you can use a program to find that for you. So that's pretty neat. Yeah, I think that's what I wanted to say about that. So that's 4 loops in a nutshell. Any questions about either of these? So you'll get all this code. This I'm going to save in the folder from last time because we started it last time. But I'll start a new folder for everything else today. All right, so let us continue. Let's actually like go over functions for real now. So okay, what is a function? The idea of a function is it's like a piece of code that you can rerun. Right? Keep on rerunning with new things. So here's what it looks like to make a function. You got to pick a name for it. Say def, give its name, and then between parentheses you give whatever it's going to take. You got to give names to those things because you need to hold on to them and like use them. So param 1, param 2, you comma separate them if there's any. Sometimes you have functions that don't take anything at all. That's fine too. You just call them, and then you have do your colon, give the body, and what you do is like you're using these values that you're given to compute some answer. All right, either you're just going to go off and do something, or you're going to return something. If you say return, remember that that's going to give an answer back so that somebody can use it in a bigger place. They can do math with it. And so once you've made your function, then you can call it as much as you'd like. You say its name, and then you give arguments for as many parameters as there are. So like you pass 42 and 43 into param 2, and then like you get those. It's going to run the body then, right? With once you say it like this, it's going to run the body with arg1 set into param1, arg2 set into param2. These are like the names that you hold on to those values with, right? And that's how a function works. And if it gives a value back, you better save it, right? Save it into this result variable. If it doesn't give a value back, like print, for example, doesn't give anything back, then you don't do that. You just use it online by itself. But yeah, if it returns something, better use that value or save it, because otherwise it's gone the second you call it. All right? So yeah, that's that. Let us talk about a silly little example. Let's do this one. This is a nice little encryption, right? Let's do the ROT13 encryption. We talked about this just briefly. It's just like stands for like rotate by 13 in the alphabet. So if somebody gives you a message, a secret message, it's also called the Caesar cipher. Remember that? Someone gives you a message, what you do is you shift every letter 13 in the alphabet, and like Z wraps back around to A as you're going that way. So it's like a clock. And H becomes U, E becomes R, L becomes Y, O becomes B. So like you send this to somebody, you send Uriab to somebody, and they're able to like undo your encryption. because there's 26 letters in the alphabet. It kind of goes right back to the original if you do it all over again, so that's perfect. It is its own inverse, but yeah, you give this, and then somebody can decrypt it back to hello. They shift it all over again. Okay, so let's make a function, or really two, that's going to do this. It's going to take a string that somebody gives us, and it's going to encrypt it for us, right? Make it all nice and jumbled. So let's do that. Let us make a rot13 function. So I'll make a new file, and I'll also make a new folder for today. So here, I don't want this here. I'm going to go on a limb and say that this is lecture 31. And I'll call this rot13. Cool. So I got this. And so here's my goal. Here's what I'd like to be able to do. I'd like to be able to, like, somebody gives me a string, like hello. Let's say it's all caps. And I want a function that, like, takes that string and does rot13 on it. All right? That's what I would like to have happen. Okay? Something like that. So that will work. And for reasons, I want a couple of them. I want like a rot13 that works on a string, and then also we'll do one that works for an individual character. And let's make this be a function that gives back the answer, the new string that is the encrypted form. So if we get it back, then we better like use it, better print it out immediately or something. Okay, so that's how I want to use this function if I had one, and that's how I want to split it up. So I want to, let's make a function that encrypts an entire string, and also make a function that encrypts a single character, because do you see how if I want to implement this rot13 string function, I'll just go through all the characters and encrypt them one by one, add them to some new string I want to give back, and that will be how I do that. So here, rot13 string, so we're given some text, let's call it text here. What I would like to do is build up a new encrypted version of this text variable. I want to go through every character of text, the H, the E, the L, L, O, and encrypt just that one character. Like take the H just to a U, take the E just to an R. That's what I'd like. So I want to build up then an encrypted string that I will start empty. And I can add to it, right? I can be like encrypted string equals itself plus some new encrypted character. We'll get to that. All right? And that's how you can build it up one by one. Because you can always add new characters to the end of a string. Yeah? It's like if I had hi, I can add to that just like hello, or I could add just a single character and be like H plus I. Like that will build hi. So I can just add one at a time. That's what I want to do. I want to encrypt a single character, add it along, and then by the time I'm finished, I'll have my encrypted string to give back. Encrypted string. And so now, how can I do this? Let's make it easier on ourselves, right? Let's pretend that we had a nice function that would encrypt just one character. Take just the H to the U, just the E to the R, and that would make things easier, all right? So what I like to do is go through. This will be part of like a body, actually. So I'd like to go through every character in text and encrypt it. All right, that's what I'd like. So you can actually use a for loop, because a string is really just a list of characters, isn't it? You can use a for loop to go through every character of a string. So like for, call it C, for every character C in text. That's going to work. And so now I have each character one by one in this original string. I want to what with it? Like I see the H, I see the E. I want to encrypt just that one character, right? Take that one character, encrypt it. Encrypted character equals rot13 on a character. Let's just pretend I have that function. Call it on C. That will encrypt, right? It will give back the encrypted form of that character. Take the E to the R, the B to the O, etc. And how do I build up my encrypted string with this? Just like, all right, tack that at the end. Does that algorithm make sense to us? Are there any questions about what I've just done there? Like I'm going through hello, going through every character of hello, encrypting the H, encrypting the E, the L, the L, the O, and adding it to the end of this big string that I want to return. I started empty. I'm going to add one character at a time to it. The new encrypted versions of things. Won't that be fun? So yeah, now I just need that function. I just need rot13 char that returns one encrypted character. All right. And so for that one, let's make that function then, because that's all I need to finish this off. Rotate 13 on a character, a single character. I'll call that character C. Whatever I got, I'll call it C. Pretend it's only a capital character. And it's my job now to, like, if I got an H, return a U. If I got an E, return an R. Just single characters at a time right now. And here's the way I want to do it. Here's the easiest way I can think about doing this. It is a complicated example, but it's a good review. So what I'll do is I'll make two lists of characters. So a list of characters is just a string. I'll make two strings, and the first string will just be the alphabet, A through Z. And then the second string will be underneath it. It will be the encrypted form of each of those characters. Watch. So here's like every character of the alphabet. Let's start it off. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T. Let me know if I forgot one. And then I will have encrypted chars right underneath it. So at each place of the string, I'll have in the same spot the encrypted version. So what's the encrypted version of A? It's N apparently. N, O, P. I need to go through the alphabet now. N, O, P, Q, R, S, T, U, V, W, X, Z. That's still correct. A, B, M. Cool. So do you see how now, with each character H, underneath it, at the same place in this other string, is its encrypted form? That's going to be our secret here. It's like, okay, here's L. Go to the same place. Find the L that was in your character. Like if your character is L, find it here. Find its index as place in this string. And then go to the same index and encrypted chars. See that? Because then it'll take us to the jumbled version. It'll take us to the encrypted version now. That is going to be our answer. So find the index of C in chars. That would be nice. So it's just going to be a loop. It's like I starts at 0. That could be the first index. Let's use a while loop this time. And the index of the character. So I need to hold on to that, right? As I ranges through all the characters. So I'll hold on to that. I'll start at -1 just because I haven't found one yet. -1 is an invalid index, kind of. So while I have a valid index, while I is less than len of chars, right? Because that's the length of all these characters, the size of the string. The last index, this is index 0 up to its length -1, right? So while it's strictly smaller, I have a good index to go through still. And then if I see that chars of I, that will give me a character, right? So let me prove that too. Like if I had a string, hello, if I go to index like 2 of that, that gives me an L. Because that's index 0, 1, 2. It gives me the first L. Okay? So I'll get out a single character. It's like if that particular character of this string is the one that I need here, if that's equal to the C I was asked to encrypt, then I found it, then the index of that character I care about is equal to I. That's what I want. And then just do like I equals I plus 1 to move along, because maybe this isn't the right one. Eventually we'll find it, right? If it's a capital character, we'll find it and save away by the time this loop is finished the index of where it lived. So like the H, it's like index 7-ish or something, right? So you got that one. And then I want to use it. So I found like, all right, this is index 7-ish, or pretend it is maybe. Maybe it actually is 7, I don't know. So like I found index 7. I want to go to index 7 of encrypted chars because that's the encrypted version. H needs to map to U. So that's what I do. Go to the same index in encrypted chars, and that will give me what I want to have happen. And that's what I want to give back. So go to encrypted chars at that same index, whatever I saved, and return that, right? That's what I want to give back. Give back the encrypted form of that particular character. And that will do it. Do you see how all these functions are playing nicely with each other? Like I want to encrypt this entire string, so I'm going to go through every character of that string and encrypt each character by asking this other function to encrypt a single character. They're all playing nicely. Isn't that beautiful? So yeah, let me try running it. Let's see if it works. Well, look at that. Uryib is beautiful. So it is doing the right thing, and I think that's a good example of a bunch of functions. So are there any questions about either of these two functions that we wrote just now? This one or this one? I just got a bunch of examples today. Let's see. If we are good, let us continue. I have a fun one that like has an interesting idea. Like the second one will be fun. The first one will also be extra fun. So here, let's use random library. All right. So don't forget about that, Python random. you'll have to remember all the functions that we used in the library. Better write those down on your cheat sheet or something. Oh, did I accidentally save a page? Oops. Let me fix that. I do not want that in my downloads folder. So, all right, random. Kind of the two functions that we really use. Some of you guys used random.choice. That's a useful one as well. Random.randint we used to get a random number integer, and then random.uniform, wherever that is. That gives you a random float, all right, with decimals potentially. So those are the two that we kind of usually care about. And so let's use some random numbers by importing the random library. And the first one is let's make like a random Etch-a-Sketch. You guys know what an Etch-a-Sketch is? It's a thing with the knobs that like it lets you draw. Like it moves up if you turn this knob, or down, and turns left or right if you move that knob. So let's make that happen in the turtle library. All right. So let's make a program with a turtle that just like randomly picks where to go and how far to go to. All right. So we'll have the turtle draw just a bunch of random lines and turn in random like offsets of 90 degrees, and that will just draw a bunch of cool straight lines. It'll be very pretty. Okay. So let's make that. I'll make a new program. I don't think we need any functions for this one, but it's still a good example. So let's see here. I would like to make which program? I'll call it Etch-a-Sketch. .py. And what I like to have happen is this. So I want to import the turtle library. I want to import the random library. And I want to use them nicely together. So I want the turtle shape to be a turtle. And remember, you can use strings that are double or single quotes. Python does not care. And then I'll just make the turtle go fast. You can say turtle.speed fastest to make him go super fast. And that will be useful for me later. So what I'll do is just at the start, just like forever, I'll have a forever loop until the end of time, until I click the X. We'll fix that in a second. Until I click the X, what do I want the turtle to do? I just want him to draw some random stuff. So like, let's have him like go forward by a random amount wherever he's going right now. Like that can be what the turtle does first. Like go forward repeatedly, go forward by a random amount, and then turn by a random amount as well. But let's make the turning be like always perfectly straight on, so it's like a random multiple of 90 degrees. That will work for me. So yeah, turtle.forward by what? By some random number. By like random.randint, like a random number between like, I don't know, 10 and 50, let's say. That will work. Oops. There. So that's all closed off. Does that make sense? Like that's what he's going to go some random amount right now. Whatever this gives back, it'll be different every time because it's random. It's flipping a 41-sided coin or something. And then turn by a random multiple of 90 degrees. It doesn't actually matter if we turn left or right now because like they'll all be an option anyway. So I'll just say turtle.left, but either one would have worked. By some multiple of 90, so 90 times random.randint. So I want like turn not at all, so like 0 degrees, 90, 180, or 270. Those are all the options, right? So 0 to 3. So do you see how if he does this forever, he's just like draw a line, turn some random direction, maybe that way, draw a line, he's just going to zoom around the page. It'd be cool. Forever. Look at him go. Well, that's pretty neat. We got some nice abstract art this way. And then eventually, it's like he's going to run off the page, and like go so far away we can never see him again. So what I'd like to do is to prevent that, because eventually he will just fly off and we'll never see him again. So just due to the way randomness works, like now he's gone forever probably. What we'd like to do to like have him just stop the drawing, don't keep going once he's gone off the page because we can't see him anymore. Let's have him like stop drawing when he runs outside of the like a 600 by 600 rectangle at 0, 0. So like if his coordinates for x, like if his x like passes outside of like negative 300 or positive 300. Same for y, right? If he goes outside of that range, he's like outside of like a little square in the middle. So I think that would be a good way to stop him. And you can get where he is with, there's a few ways to do it. You can get his coordinates in one fell swoop if you'd like by turtle.pos or turtle.position. Oh wait, this is a random library. Python turtle. So you can get his position. Oh man, every one of these examples is using position. So you can get his position with .pos, .position. And then, where is a list of all of the things? There they are. So where move tells state. So here you can get his position all at once with position or pos. And then if you just want a single coordinate, you want the x coordinate only, you can say x core or y core. Let's use those maybe. That's a thing we haven't used before. So like as long as I want to keep the turtle moving, as long as he's within these bounds, while his x and y are within that range. So here's what I can say. Just like while the turtle is in a good spot, while he's not off the screen, while his x, like turtle.xcore, is between -300 and +300. And this is a cool thing you can do in Python. You can't really do this in other languages. But like you can do like this doubled up mathy kind of like give me a range with some less than or equal to's. That's really nice. It's like, well, that's true about the x coordinate, and the same kind of thing is true about the y coordinate. Boop. Then he's within the bounds that I care about, and he can keep drawing there. So while this is true about his x and y, keep going. Otherwise, the second he goes out of this range, it's just going to stop the while loop, and the program's going to be over. But the beautiful picture will still be on the screen. You can see it like, you see how it kind of moved it back here. So it gave me control again, which means he flew off a little too far. So yeah, each time it's something random and different, and that's a good first example of the random library. Get some cool abstract art this way. And now he's gone forever. So then it stopped the program because of that. So yeah, I think that's what I wanted to say. It would be extra fun to like play around with these. Because like if he doesn't move as much, 10 to 20 for example, then he'll probably stay in the middle longer, won't he? And he's going to make smaller little lines because of that. So it's cool to think about, but yeah, it's just a fun little program to show the random library. Are there any questions about why this code does that? That's exciting for me. All right, so the next one is going to be a graphical explanation, but I'm not actually going to draw pictures with the turtle library. This will be fun. Let's make a program that calculates pi. How could you do that? There are plenty of ways. I'll show you an easy way. It's not going to be the most accurate in the world. You have to do it for a long time to get it super accurate. But here's a fun idea. You can approximate pi with randomness. All right. What we'll do is we're going to make a simulation program. We're going to simulate throwing darts at a dartboard, all right? And just based on how those darts randomly land, we will discover some digits of pi, surprisingly. So here's the setup. Here's how you can discover pi with random dart throwing. It's a very interesting idea. So here, let's say that we've got a frame. And inside of that frame, we're going to have a dartboard. It's just going to be perfectly touching that edge there. So we got a dartboard, and we also have like this outer frame. So this is let's say that this is just to make up numbers. Let's say this is a radius 1 dartboard, and that means this little box around it would be a 2 by 2 if it just perfectly touched it, right? This is a 2 by 2, and let's say that this is at like 0, 0. So there's 0, 0 in the middle, 0, 0, which makes this like y equals +1. This is y equals -1. So like pretend this is on a graph, and this is x equals -1. This is x equals +1 right here. So like we can set that up if we want to. But what we can do now is ask the random library for 2 coordinates between, like the x and y can be between -1 and +1. Do you see how that will give me a random spot within this square? All right, give me a random x between -1 and +1. Give me a random y between -1 and +1. It's going to be some spot here now. And that spot, that random spot that I generate, will either be inside of the dartboard, right? Or it'll be outside the dartboard because some of those points are not within that circle. yeah, but they'll all be within the square at least. So sometimes it'll land within the dartboard, sometimes it will land outside of the dartboard. And what is the probability, if this was truly random and the random library tries to make sure that it is, if these coordinates that we're generating, these darts that we're throwing are truly random, what are the odds that they hit the dartboard? It has to do with a ratio of areas, doesn't it? It's like it's more likely, like we're going to hit this dartboard with a ratio of the area of the dartboard itself, right, over the ratio, over the area of the whole thing, the whole place where we're throwing stuff. Does that kind of make sense? Like, all right, the odds that it landed here is like however big this area is over the total area, right? What's the fraction of area that is the dartboard? Because that's how randomly we're going to get there. It's more often if there's a bigger fraction. So what is the area of the dartboard? Well, it's pi times 1 squared, right? So it's just pi. So that's the area of this dartboard. And what's the area of this square that's bounding it? It's 2 by 2, right? So it's 4. So the odds that a random dart hits the dartboard is pi over 4. Does that make sense? And so that means we're going to get, like if we count, we throw like 1,000,000 darts randomly, we will approximate the number pi over 4 randomly. It's beautiful. So we'll get a good approximation for pi over 4. If we want an approximation for pi, then just take the number we get and multiply it by 4. Won't that be cool? That's pretty neat. All right, so it's like count the number of darts that hit inside the circle and divide it by the number of darts we threw. We know what the ratio should be that's going to approximate. If we throw infinitely many darts, it's going to be pi over 4. So if we throw just like 1,000,000 or so, we'll get a good approximation for pi over 4. So if we multiply that by 4, we'll get pi. So that's the secret. That'll be fun. So it's got a cool graphical idea behind it, but I don't have to draw any pictures. Like it's not going to be the turtle library. I guess you could use the turtle library if you wanted to like draw each dart as it goes, but it's faster to just do it with the library itself. I'll call this darts.py. So here, I would like to import the random library. And then I'd like to throw a certain number of darts. So like total darts that I want to throw is 1,000,000. Python can do it pretty quickly. And then I want to keep track of how many darts I threw randomly that hit inside of that circle. Right? So darts inside circle or the dartboard, however you want to say it. So it starts at 0 because we haven't thrown any yet. And this will just be my little count. All right. So like forever, I want to throw this many darts. So I'll just do a for loop for I in range this many total darts. I'll just like I'm not going to use I for anything other than just like iterating. So this loop body will run exactly total darts times however many that is, 0 through this -1. Doesn't really matter. What do I want to do each time? I want to throw a dart by randomly calculating some coordinates in the way we talked about, and then see if it landed inside the circle. All right, inside the circle. So throw a dart. That's easy. So like calculate the x-coordinate of the dart. It's random.uniform between, like give me an x-coordinate between -1 and 1, give me a y-coordinate between -1 and 1, and I'll get a spot on the graph. So between -1 or -1.0 and +1.0. So there's that one, and do the same for y. So get a y-coordinate by doing the exact same thing. A random number between -1 and +1, and that will now give me a random spot in that box. Sometimes it will be, a lot of the time, right, it will be within the circle. So let's go there. Let us see. How can we check now if the dart that we just threw, this x and y coordinate, how can we see like if this right here is within the circle or not? What you can do is you can ask for the distance of this coordinate to 0, 0. What is this distance here? Boop. You can ask, what is this distance right there? And the way to do that is you take your x-coordinate squared, plus the y-coordinate squared, and you can take the square root of it if you want to, but it kind of has to do with the graph of the circle anyway. It's just like, if the radius, if the distance from here to here is less than 1, less than or equal to 1, do you see how it's smaller than the radius, so it must have been inside the circle. But like the distance from here to here, it's bigger than 1. It's like 1.2 or something. It's a little bit bigger, which means it must be outside of the circle. So I just take the distance from the center of the circle, 0, 0, to that point that I drew, then I'm good. I just want to check this. So if you do the math, it's going to be like, check if x squared plus y squared is like, it's on the circle if it's equal to 1, and it's within the circle or on the circle if it's less than or equal to 1. That's what you can check. So that's like that's the equation for a filled in circle right here. So that's what it means to be on that circle. Isn't that cool? It's like if that's true about my x and y, it was in the dartboard, it was in the circle part. Otherwise, if that's not true, it was not. It was outside. And that's all I check. See if it landed within the circle. By doing that, I'm going to need to do some math now. So if x squared plus y squared, so x times x plus y times y, x squared plus y squared, if that's less than or equal to 1, then it was inside. So darts inside circle. I got one more now. I found a new one. I threw a good throw. And so now I've got all this. It's working. By the time this loop is done, I have thrown now 1,000,000 darts, or however many total darts was, and I've got to count for this. And I can do this calculation now. Take that number of darts that hit inside the circle. That's this number, right? Take that. Darts inside circle, divide it by the number of darts that I threw total. That's just total darts. And that's an approximation for pi over 4. If I multiply the answer by 4, I've now got an approximation for pi itself. Cool. And so I want to print out whatever the result of this is. And let's watch it work. Let's see how good of an approximation for pi this is. It is not the world's best algorithm for discovering pi. There are much better algorithms that discover pi faster, but this is an easy one to explain. So it's running, it's trying real hard. And look, we get it to a decent number of decimal places. We get it to at least 2 decimal places. There's my approximation of pi. It's not exactly pi, because it's dependent on randomness and all that. But if I rerun and I get a new approximation for pi, it's always pretty close to at least 2 decimal places. If I throw 10 million darts now, it'll get a little bit better, maybe to another decimal place. This is what, 3.1415, right? 3.1416 if you do that. It'll take 10 times as long now to run though. 3.141. Oh, we got it to 4 decimal places. Oh no, maybe just 3. Nice. We got to 3 decimal places, at least almost to 4. Beautiful. And it'll be better or worse depending on how you run it, because you're at the mercy of randomness. But on average, it's going to be pretty close. It's not going to be like 4 point something usually. So yeah, it's at least 2 decimal places or 3 decimal places if you throw 10 million darts now. So it takes a while to actually converge to something like with a lot of decimals, but I think it's a fun little example. Are there any questions about that? This is an example of loops and randomness. That's one way to discover pi. It would take a very long time to get a good answer this way, though. There are better ways. But I think it's fun still. There's that one. Yeah, if we are good, I have a couple more examples. This will be functions plus turtle library stuff. So I would like to draw a bunch of different target logos. All right. So the backstory here is when I went to grad school at UC Santa Barbara, there was no Target. You had to drive to Ventura if you wanted to go to Target. It was an hour away. It was disgusting. The only larger store in the area when I was going there for my first 4 or 5 years was Kmart. It was the largest grossing Kmart in the country, the second largest grossing Kmart in the country, because there was nothing else around. It was disgusting and horrible. The only other Kmart that made more money in the country was in Hawaii. That's how little options that we had there. And so once Target came, it was wonderful and everybody loved it. And so now I'll just pay homage to that. All right. So here, let us make a rectangular Target logo, and then we'll make a circular one as well, and then like a triangular one, just to see how it all kind of goes together. All right. So let's make a bunch of functions to draw this Target logo. All right. So the square way will be the easiest way. Do you see how I could draw this Target logo? Oh no, have I lost my... Oh no, it's back. You see how I could draw this Target logo? If I first draw this outer red box, make it red. Then if I draw an inner white box, it will cut out a piece of it. And then if I draw another smaller red box, it will fill in the white part. See how if I did all those 3 things in that exact order, I would get my little rectangular Target logo? So if I did it that way, then I'd be good. And now the question is, how do I just need a draw square function, right? I need a draw square function that figures out how to draw this particular box. So the color is going to change, so color better be a parameter, better be an argument, potentially. And then one way to represent the idea of a square is give me its center coordinate and give me how big of the box it is, yeah? give me the width, give me the color as well. I'll just use the begin end fill. So apparently the good numbers that I came up with before is like 200. If this is a size 200 box, this is a size 125 white box, this is a size 50 inner red box, that'll do it, right? But we know to draw a square, we need to be at the corners, right? We need to calculate the corner coordinates. So if we're given the center this time, instead of like the upper left, how do I get to the upper left from the centers? Like if this is the center, how do I get to the upper left? Because somebody gave me just like these, right? I get the width, I get the center. I can use this to calculate the upper left, right? Can't I? Because like all I need to do, if I'm given the center, if I go left by half of the width and go up by half of the width, do you see how that would get me to the upper left? And now I'm in a corner and I can actually draw a box like the turtle knows how to do. So I can use my center coordinates to calculate the upper left coordinate. All right, so that's fine. So my upper left coordinate is equal to, well, start at your center, like start at centers x, center x, minus, go left by half the width, so minus width over 2. That'll be your x coordinate of the upper left. And then the y coordinate of the upper left is, well, it's center plus half the width. As you go up in the y direction, take center's y and go up width over 2. See how that will calculate your upper left? And that is what we'll do. So that, remember that the center here, what we were given, that's from the user, that's center, whatever it is, it's some variable. Center x and center y is what I'll call it. Okay, so that is how we can draw some squares. And if I make 3 calls to that function with the right colors, I will get my target logo. All right, let's do that. So that will be a new file. And I'll call it target square. I will make a, well, I gotta include the turtle library, of course. The turtle better look like a turtle. That will bother me otherwise. Turtle.shape turtle. And then I like to make, if I made 3 calls to my draw square function, I would get my thing. Which ones does it need to be? It's need to be like draw, if I had it, draw square, centered at 0, 0, let's say, middle, right in the middle. With 200 first, and that's the big red box, and then do 2 more of those. Do an inner one that's 125, that's white, and then do an inner one that's only 50, that's still red. All right, so they're all centered at the same spot. But if I do those in that order, I will draw my thing. Okay, now I just need to make the draw square function. So let's do it. So draw square, the job of draw square is to do just like this. Def draw square. It's going to take a center point, a width, and a color. And the center is going to be given as this thing. So like a list is called a tuple, remember, if you use the parentheses instead of the square brackets. So how do I get the pieces of it? Because I want it like the center x, I want the center y. Those 2 bits. Well, those are just indices, right? If this is a thing just like a list, this is the thing at index 0, this is the thing at index 1. So center's x coordinate is equal to, take the center tuple, go to index 0 of it. It's just like a list. Same for center y. It's going to be at index 1. It's the next thing over. Center at index 1. So go there, and then I can calculate my upper left coordinate from those. It's exactly these. So from the center, I can go left by the width and up by the height. So upper left is equal to center x minus width over 2, and then center y plus width over 2. Those will be the x and y coordinates of the upper left. And now I can draw my square. I can tell the turtle, hey, all right, turtle, I'm ready for you to take over. Let's turtle dot go to that upper left corner. All right, just go to that thing that I've just calculated for myself. But I don't want to make any marks as I'm going there, so I'll say turtle dot up, right? Turtle dot up to get there. Now I'm in position. Now I can say turtle dot down. And then when the turtle's in the upper left, who knows where he came from? He could be facing some weird direction. Who knows what we did before? So we want to always make him face that way so we can like start drawing the square in a normal direction, right? So to set him this way, to face right, that's east, we can use the set heading function. So that's turtle dot set heading. And it's 0, apparently, is straight right to the east. And so that now we know he's always facing right, and now we can go forward, right? Go forward by the width, turn right by 90, go forward by the width, just play that game. I'll get my square out of the deal now. So okay, turtle, go forward by the width, and then turn right by 90, and just keep on doing that 4 times. Boop, boop, boop. I don't really need to turn right 90 the last time because he's already finished at that point. All right. Does everybody see how that's going to draw my square? I haven't filled it in with colors yet, but let's see if that's good enough for now. So let's make sure it's actually drawing the squares. There's the outer one. There's the inner one. There's that one. For weird quirks of the turtle library, if I zoom in, it goes away, but I don't know if you can see it. Like, it's jagged when it's like this. But it's really fine. We did it right. It goes away. But now we just need to fill them in. All right, so let's fill them in by using whatever color was passed to us. So the way that we fill things in is we set, right, it's going to be turtle.fillColor. If you want it to be red, you set it to red. If you want it to be white, you set it to white. So just set it to whatever color was passed to us. The user knows best. And then to actually fill in, right, a shape that you're building, you got to wrap it around begin and end fill. So you say turtle.begin fill. And then once you're done drawing, once you close it off, you let the turtle take over, and then you say end fill. Yeah. You got to make sure to set the fill color before you start, though. That's important. Or at least probably before you say end fill. So now I'm actually using the colors that were passed to me. Whee! And so you see that the turtle has changed color to reflect that. I got my red, then my white, and then another red. And it's a beautiful square target logo using my draw square function. I'm calling it 3 times. Are there any questions about how I made this program? Make enough sense? It's a good example of a function. So this is a function you just call on a line by itself, right? It doesn't give anything back. That's quite nice. So let's do the circular target logo. So, and eventually we'll generalize this to even be a triangular target logo, so that'll be fun. So let's do that. All right. So if you want to draw circles in the turtle library, let's say you kind of have to start it's not in the center anymore. You got to be down here. So if somebody gives you the center point of where your circle should be, then you got to move down to here because the turtle library wants you to be at the bottom of your circle. All right, that's how you draw a circle with the turtle library. Got to be at the bottom, and then you say, oops, it's legitimately turtle.circle. You say turtle.circle, you only need to give one thing really, and that's going to be the radius of the circle. And what that means is how big of a circle do you want to draw? So what is the radius of it? So it's half of the diameter, right? And then the rest of this controls whether or not you want the circle to go all the way around. We don't need to deal with that. So yeah, we'll just say whatever we want it to be. We can calculate the radius very easily. We can get that passed to us if we need to, but that will draw a circle. All right. But you got to start the circle. If you want it to be at a certain spot, you got to get down to here, and then it'll draw the circle centered around there. Okay, that's how that works. And so let's take our program and make it better. So we'll take the square drawing target program, make a new file, and I'll call it target improved, closer to being right. I'll keep this draw square function because we're gonna need that. I'll just get rid of this stuff. I'll comment it out is what I'll do. There, so it's not gonna draw the square target logo again. But do you see if I had a draw circle function, I could just do this kind of? Because it's kind of the same idea again, isn't it? Just instead of squares, it just draws circles instead. Same idea. So if instead of being draw square, if it was draw circle, centered at 0, 0 with this width, starting with red, then white, then red. Do you see how I would get the target logo? Instead of this, do that. If I had to draw a circle in the same kind of way, it would be happy. So let's do that. So draw square. Instead of that, I'll call it draw circle. And most of this needs to change, but I'll just copy most of it for now. So if I have a draw circle, I'll still be given a center, a width, and a color. So I need to get, this is my center X and center Y still. I need to get down to here from center X and center Y. Well, how do I get down? The X's stayed the same, right? It's only Y that I need to move in to get down to that spot. So this is this will be width over 2, right? Because the width is really the diameter if you're talking about circles. So width over 2 gives you the radius. We need to use that. So go down by that. And this is center, same x, but go down in the y by width over 2. Bless you. So center y minus width over 2. And that will give me my coordinates of the new center, or the bottom little corner of the circle. And that's where the turtle wants to be to draw things. Okay, let's do that. And so keep that, and it's not upper left anymore. Now it's just like bottom. I'll call it starting point. Starting point of my circle is going to be the same x as the center, x, and then it's minus width over 2 here this time. It's like go down by the radius amount. And then we still need to get to the starting point. It's not called UL anymore, it's called starting point. I don't need to worry really about the heading, but I'll just set it to 0 for fun. And then the fill color stays the same, and that's begin, fill, end fill, and we draw a circle. Now, we say turtle.circle of a given radius. So how do I get the radius from the width I was asked to draw a circle of? So the width is like the diameter, so the radius is width over 2. Yeah. And that is how I can make the draw circle. Does that make enough sense before I show it? You can see how that all filled out together. It all came together properly. Now if I run it, see how it gets to that right spot. I'm drawing this little circle. Red circle, then a white circle, then a red circle. Ta-da! Now I get a turtle right there, comes along for the ride. Isn't that fun? I think that's fun. Are there any questions about why that's doing it? Same idea, right? Using a function, calling it pretty much the same way to make it work. I love that. And just for fun, let's do a triangular target logo. All right, why not? Triangular target logo time. So let's see. What I would like to do is this one. And so I think you can imagine, if only I had a draw triangle function, then I could do all this over again, right? If only. I would say draw a triangle here. Boop. Just like that, just like that, just like that. Instead of draw a circle, comment that out. If only I had these, I could make it work. Let's make it happen. So I guess I'll start from draw square because it's closer to what I want. So again, we're given, all right, the center point of the triangle this time. Draw a triangle. I need to find let's start the triangle, maybe, I think we usually have started the triangles in this class down here. So somebody gave me the center point of the triangle. I need to get to the bottom left part of the triangle, all right? The way to do that is you go down by, it's not half of your width. Let's say that the width is this length right here. So it's not, you don't go down by half the width. It's actually a third of the width. Triangles are weird. Equilateral triangles are weird. I had to figure that out. A student helped me with that once upon a time. And then you go over by half the width. Go left in the x direction by half the width, but go down in the y by width over 3. That gets you to your bottom left corner. All right. So that's kind of what we need here. So it's not UL, but BL, bottom left. It's going to be, the x is going to be go over by half the width. That's still fine. But the y, it's go down by a third of the width. It's very odd. All right. And then we're here, we go to that BL place, bottom left. Set the heading this way so that we're facing this direction. And then what I can do is I can go forward, right? Go forward by the width. Then I'm this way, turn left by, remember it's got to be 180 minus the 180 minus 60 because that's the angle of all of these angles in an equilateral triangle. Remember that, right? And so just keep doing that. So let's go forward by the width, turn, it's a left turn this time, right? Turn left by 180 minus the angle inside, so minus 60. So what is it? Supplementary angle. Correct me if I'm wrong. And that's what you keep doing. So it's always do those things a bunch of times. It's 3 times, right? 3 times. So 1 side, 2 sides, 3 sides. Got to keep it all indented. You don't have to turn at the last one. You've already finished it off. And then you're good to go. So that should be a triangle in theory. And I'm calling it 3 times with the same kinds of widths and colors. I'm just saying draw a triangle. Well, let's see how that works. Oh, it's so satisfying. Yay. Are there any questions about why this one's working? It's all the same as the other two, right? I'm calling it in the same way. It's getting those values. It's using them. It's happy. You could have centered it anyway. We're just using center 0, 0 all day long. We'll change that in a second. But that's useful, right? So we got a bunch of functions that kind of work the same, right? So yeah, we figured out that this was the bottom left. Honestly, I kind of want to do it in this order. Let's do it. We did the triangle. Now let's do this. Let's generalize our program. Something like that, all right? So notice how, if I want to draw a square target logo, I run these 3 lines. If I want to draw a circular target logo, I run these 3 lines. If I want to draw a triangular target logo, I run these 3 lines. This should scream repetition to you right now, right? There's got to be a better way, right? There is. Why don't we just make a function that draws a target logo and we'll run these 3 lines however we need them, whatever shape we really want it. So here's kind of the end goal, if that makes sense. Let's generalize what we're doing here, because it's always those 3 kind of calls, right? Let's make, instead of like draw a triangle, draw a circle, draw a square, let's make a function call to like draw a target logo, right? Give it a center, like 0, 0, and then give it what kind of way to draw the logo, right? Do you want to do it with triangles, circles, or squares? We can just pass that too. It's like, all right, draw it with squares. Does that make sense? And then just like this becomes it all now. Just like one line for the target logo that you really wanted. It will take care of calling these in the proper way. That's what we want here. All right, so that's my final function. Make a function that when we call it, it does one of these. I'll say def. Here, let's move it up so you can see it. Def draw target logo. What do we need to draw a target logo? We need a center point for the target logo. We know the widths are hard-coded at 200, 125, 50. We'll do that ourselves. And then the colors, we know those too. We'll hard-code those. And then the only other thing is like, how do we want to draw the shape for the target logo? So we need a function, right? Draw shape. Whatever that is that we were passed. So we'll pass like draw square, pass draw triangle. We can pass a function to a function. So I'm getting the name draw square up into draw shape. And so draw shape now is a function that I can call. Does that make sense? It's just it's a variable name for a function now. I can pass a function to another function. We did that with like the paddle program. It's a very interesting idea. So now I just want to say, right, instead of this a bunch of times and this a bunch of times, it's just like, if I want to do a square target logo, it's not just this anymore. It's not a bunch of draw squares. It was, I want to draw some generic target logo with some particular shape drawing function. It was this one that I was given. Use it. Draw shape, draw shape, draw shape. The center point is this one, whatever I was given. So use that center point wherever I wanted it to be. And then it's always 200, 125, 50, and then red, white, red. But does that kind of make sense of what's going to happen when I call this line? It's going to jump up to here with center 0, 0, and draw shape will be set into draw square. So now when I say draw shape, I can call it like that function, right? It's going to take those 3 things still. Like draw shape for the duration of this particular call, it is draw square. Isn't that neat? I think that's really, really cool. It's a very powerful idea. I don't really even get to teach for the first few major level computer science classes. So it's very cool, all right? So that's what I wanted to say there. And now I can draw a bunch of target logos. Like this one doesn't have to be centered at 0, 0. It'd be like at 150, 150. That can be a square target logo. Now this one, watch what's going to happen. So like it's going to do the same thing properly. It's going to jump up to here. That's my center point. It's going to run these 3 lines with draw shape being draw square. It's perfect. And I can do this with a bunch of different ones. I can do this one. I can do this one. Let's have a circular target logo at -150 centered there. Draw a circle is what I'll pass along. So draw shape will become draw circle for this call. That's what it will become, and it will draw with circles. And then finally, we can have a triangular target logo if we pass draw triangle. And the only other thing we need to pass along is like to control where that thing's going to be. Let's center this one at 0, 0 finally. So now I'm making 3 target logos. Each of those is just a single line now because I've generalized this idea of what it means to draw a target logo at a given spot with a given shape drawing function. That's what parameterizes the target logo, and that's why these are called parameters. Cool. So there's the square one. there is the circular one, chugging along. And then right in the middle is going to be the triangle. Nice and generic, probably as good as we can make it. I think that is what I wanted to say. Are there any questions about that? This is a great example to study, I would say. It's like a good example of like taking functions, making more functions, thinking about what you really needed at the end of the day. So yeah, you get some pretty target logos and a turtle at the end of all of this. All right, so yeah, this would be some good code to study, I think. All right, in the remaining time, I got a couple cool examples. I want to steal them, though. Give me a second to take them. They're pre-made. They're long, and so I need to get them from somewhere. Can I hide all of these windows? It's way too many of them. I need to go to the desktop real quick. Oop, oop, oop. Go that way. So here's our code from class. I want to steal a few files. The first file here is here. I need this. Can I go into a different window? No, not easily. I guess there. Here's the folder where we're working today. And then here is a file I made in my CSCI 40 class. Yeah, I got this one. I want to show you that. And then I have another one from a previous semester's CSCI 1. I'll go to, I guess it was S25. This lecture. I want this one. All right, so I got two files now that I've just added to today. And let's talk about them. So I just want to show you the extent that you could go with the turtle library. This is some hardcore code that you're about to see. You do not have to understand any of it. It's just a couple cool examples so that you can kind of see like where you could go if you learned a little bit more computer science, if you learned a little bit more programming. So yeah, the first example is this one. I want to make a program that draws this kind of artwork inspired by the artist Pete Mondrian, right? We've seen these before in theory, but it's a fun little example. We'll use some functions to do it, but at the end of the day, how do you make this kind of art? Maybe randomly, right? It's just a bunch of squares all over the place, right? That kind of interlock and align. Here's my silly algorithm, all right? I've made, let me show you the program first. You can watch it run, and I'll prove to you that it like kind of looks like that. It's this one, PeteMondrian.pile, edit with idle. If it wants to open, at least. There it is. So yeah, draw a rectangle function, draw a line function, pick a random color function, like all these things you could understand, right? And then here's a Pete Mondrian function, and then I do some things. So here, those are all those. Dun, dun, dun. If I run this, dun, 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 it's printing cool things, printing out information. But look at it go. It's picking random colors, little bits off the screen, and then it's drawing random little squares, and they're all aligned properly. Sometimes they're bigger, sometimes they're smaller. It's more or less a thing, right? That's pretty cool. So let me try and explain how this code is working. It is a recursive program, first of all. So it's a function that calls itself at a smaller value, because if you think about it, if you zoom into like half of this artwork, it's still a similar artwork, right? So you've kind of found it inside of itself. That's what it means to be recursive. Again, I won't ever test you on this, but it's a cool idea. Like, I want you to understand it. And if you rerun it, of course, it'll be a different random looking piece of art. So like we'll have it do that as I talk about it. So like first step is like I set the turtle to draw some thick lines, and then it's recursive, right? Now it's recursive. So initially, like I make a call to my little functions. Like here's my draw artwork like Pete Mondrian function. I give it the bounds of the window where I want to draw. Like here's my min x, my max x, my min y, my max y. So like from here to here, from here to here, like set the whole window that I want to draw it on. So now I've got the whole space. And then I section off the window. Now I'm like, I pick, I flip a coin essentially. What I do is what I'll do is I'll split the problem in half on one of these directions. Like I'll split it halfway this way, for example. And then what's happened now is I will recursively draw an artwork this way in this bound and draw an artwork in this bound. It's like two calls to the function kind of. So you can either split it vertically or horizontally. So it's like it's flipping a lot of coins here. It's like, all right, either I'm going to split or I'm going to draw a square right now. It's like if I choose to split, I need to split either horizontally or vertically. Sometimes it's so small I don't have a choice anymore. Like those are your base cases of the recursion, if you remember that word. And then it's like sometimes, like I've zoomed in so far, like I've cut off the square so much that like now I'm here, and I flip a coin. Do I split or do I draw right now? It just chooses to fill in whatever is there. It fills it in with red. And so that's how it does it. All right. So it's essentially draw a rectangle a bunch of times. And it builds cool looking abstract art. Sometimes it's bigger, sometimes it's smaller. And it picks a random color for its square every time it chooses to draw like a square within its current bounds. But that's more or less what that is. Does that make a little bit of sense? Like you could do that one day. All right. Stare at the code. I'll give it to you. And then the final thing that I wanted to show you is here's a silly little program that draws this logo from the Joy Division album. Some people wear this shirt. I've seen it a lot of times. So like this cool piece of artwork is technically, I mean, it's pretty. It is art technically, but it's just data at the end of the day. I don't know how much you know about this, but here's a silly idea. Edit with idle. So this album cover is it's actually it's a signal. It's an oscillation signal from a pulsar out in space. I'm not a physicist, so I don't fully understand what those words mean, but there's a Wikipedia page for it. Here's the pulsar, and some dude doing like their graduate work took some readings of this pulsar, because what it does is it emits radio waves. They took the readings of it over a few pulses, and they just kept track of the intensity. That's all they did. So here is that signal that they took from the 60s or something. Like here's the intensity of this pulse. Like it started at this level, got a little bit smaller, got even smaller, and then it went up. We can draw this. That's what this drawing is made of. It's like, all right, if the signal went down a little bit, like you're drawing a graph, you're always moving over. It's like, all right, start here, then it got smaller, so move down. It got smaller again, so move down some more. Oh, it got bigger relative to negative 1.09. So now we go up a little bit. Oh, it got less small. It got also bigger, so even more big. So like we're gonna draw a bigger peak. Moving over. It's just a graph essentially. Like draw this on a line, draw this on a line, and they kind of overlap in a cute way like this. But that's pretty much how it works. It's like I made a bunch of functions. I didn't draw a rectangle, drawing polygons really because it's a bunch of connected lines. Draw a fuzzy line is kind of where it does the real work. Like go through the entire oscillation signal for a particular line, do things. You do have to be careful about like overwriting previous things, because once you get into the middle, like whatever was there has been overwritten now, so you have to like overwrite it in black. So it's a begin fill end fill kind of thing. But yeah, it's just like it's looping through this signal, and like that is a publicly available thing, so we can exactly draw this. It takes a while because it's a little bit of a complicated thing, but there it goes. It's off to the races, and it's able to perfectly recreate this by just like taking that data and like every time the signal went up, nudge the turtle up. Every time the signal went down, nudge the turtle down. And then also remember to overwrite everything as you're making new lines. It needs to remember to do that, of course, because otherwise, like these things in the middle, they would all just be jumbled together. I guess the cool thing about the pulsar is like it's got the biggest pulse in the center of its stuff. And so, yeah, it's just another program with a bunch of functions that I made to do this in the way that I thought to make it. And that's pretty much it. So yeah, you can look at this code. I can help you with it, but it's just an example of what you could do. All right, where you could go. And eventually, once it finishes, you'll have a beautiful piece of artwork with also a turtle at the very bottom. Come on, Mr. Turtle, you're almost there. I forget exactly what it looks like. Is it done? But yeah, that's another thing you can do. Does that make sense? A little bit of sense at least. So yeah, that's where you could go one day. And you get the added pleasure of a tiny little turtle at the bottom right once it's finished. So yeah, that's that example. And I think that's really all that I have. If you have any more questions, please ask them to me. You guys we got like 2.5 minutes. Feel free to ask me after class as well, but we might as well end the thing. So yeah, we've made it. Thank you all for putting up with me. We've made it to the end of class. Do not forget when the final is. It's on Monday at the normal time of classes. So don't forget that. I'll send you some reminder emails. And then the very last thing that I wanted to say to you is I want to try and convince you, maybe if you like what you saw, like the goal of this class is to convince some people who are not yet computer science majors to become computer science majors. So if you guys like what you saw with programming part of class especially, you might do well as a computer scientist. So consider it, and I think that's all that I wanted to say. So yeah, that's a wrap. I'll see you guys at the final day.